In today's video, what we're going to look at is the topic of the double angle formula when it comes into trigonometry. Now, we've covered what happens when we look at angles and we look at various formula involved with angles when we've got two angles combined, so an A and a B. What we're going to do is we're going to take this a step further and look at expanding these formula in a different way. Now, there's a couple of key formula we should already know, and that's these ones here. So we should know sine of A plus B, sine of A minus B, cos A plus B and cos A minus B. These are four fundamental trig formula that we are going to need to know, learn and love all the way through higher. Now in each of these, A and B are two different angles that are combined together in one of these forms. To get the double angle formula though, and to investigate that a bit further, we've got to ask ourselves one question. What happens if A and B are the same? What happens if we make both of these angles the same, and how does this work? Well, obviously if A and B are the same, this one here would become sine of A minus A, which is sine of 0, which is 0. And this one here would become cos of A minus A, which is cos of 0, which is 1. So looking at it when we're looking at the two subtraction forms doesn't really tell us anything. However, if we look at the two addition forms, what we actually do is we can generate a couple of new formula. So let's look at these one at a time. So let's imagine I look at the first formula, which is the one that was sine of A plus B. Now again, in this case, let's imagine that A equals B. What that means is I can write it as sine of 2A. Sine of A plus A, so I've got two of these there, sine of 2A. Now remember the expansion that we had before. So sine of A plus B was sine A cos B plus cos A sine B. Expand it the same way. The only difference is that we're looking and imagining we've got sine of A plus A. So we end up getting sine A cos A plus cos A sine A. A and our B all become just A's. So sine A cos A sine B. Now A. Now these two are the same, so all in all we end up with 2 sine A cos A. And that gives us our first set of our double angle formula. What we're able to say then is sine of 2A equals 2 sine A cos A. Now there's one of our other key formula we're going to work with here. Sine 2A equals 2 sine A cos A. Okay, that's the sine one. Let's imagine what happens if we look at the cos one. So imagine we look at cos of A plus B. And what we're going to say is that A equals B in this case. So we're going to look at cos A plus A. Now again, A plus A gives me cos of 2A. And think back to the expansion of cos of A plus B. It's cos A cos B minus sine A sine B. But in this case, A and B are the same thing. So if we expand it, we'd get cos A minus sine A sine A. Now cos A gives me cos squared A. Sine A gives me sine squared A. So I get cos squared minus sine squared. So I get cos squared A minus sine squared A for the cos 2A. Now, that's great, we've got a new version of that. However, this could come into play and be a bit more handy if we were able to write this entire thing in terms of either just cos or sine. And in order to do that, we have to think back to one of our fundamental trig formula that we learned back in National 5, where we know that cos squared plus sine squared is equal to 1. Now if we were to choose to eliminate cos squared or sine squared, we could rearrange this to get a form for it in terms of the other trig function. I.e. we could rearrange it and say cos squared equals 1 minus sine squared. Or similarly, get sine squared A equals 1 minus cos squared A. So this gives me a way of taking this and putting it in terms of either of these functions on their own. So let's imagine I substitute in for the cos squared. I would end up getting 1 minus sine squared A, take away sine squared A, which would give me 1 minus 2 sine squared A. Imagine I then looked at a version where I substitute in for the sine squared. I would get cos squared A, take away 1 minus cos squared A within a bracket. So that'd be cos squared A, take away 1, be then minus minus, which would give me plus cos squared A. So that would then give me 2 cos squared A, take away 1. So what I'm actually able to do is not write just one version, but 3 versions for this. I'm able to say then that cos 2a equals cos squared a minus sine squared a, so a version involving both trig functions, a version involving just sine, so 1 minus 2 sine squared a, or a version involving just cos, 2 cos squared a minus 1. So I'm able to write it in any of these. Now this will come in very handy because what it will allow me to do is take a trig function or a trig equation, something we're going to look at in one of our later videos, and write it in terms of sine or cos, so it makes it a lot easier for us to solve. As I say, we'll look at this in a slightly later video. What we're going to look at with this one though is I'm going to look at an example of how I can use these expansions to write something as an exact value. So let's imagine I'm going to take this scenario here. Imagine if tan x equals 4/3, find sine 2x and cos 2x. Well, tan x equals 4/3 harks back to our exact values video. What we do is we use this to set up our triangle and get our values so that we can set an exact value for x regardless of which trig function we want, and then we look at expanding it and using it. The first step is to get that triangle. So we draw ourselves a little right angled triangle there, and we set our angle x. Now we know using SOHCAHTOA that tan is opposite over adjacent, so the opposite side from the x is 4, the adjacent side is 3. And to find the missing side we use a good old friend Pythagoras. So let's say this missing side, we're going to call it the letter a. We know that a is equal to the square root of 4 squared plus 3 squared. 4 squared is 16, 3 squared is 9, 16 plus 9 gives you 25. So I know that a is going to equal 5. So I've got all 3 sides of this right angle triangle here. I'm able to write sine, cos and tan as an exact value. So now I can look at expanding these. So let's imagine we look at the first one, sine 2x. Now I've got sine x. I can't use 2x. I can't just multiply that by 2 and get an answer. So I couldn't do 2 times the 4/3 and get 8/3. That just wouldn't work. What I have to do is use the expansion we just covered to write it in terms of sine x and cos x, and then get their exact values from here. So I know sine 2x, using an expansion, is 2 sine x cos x. So I'm able to use this triangle, take an exact value for sine x, an exact value for cos x, and substitute them in here. So using the triangle, I can write down what sine x is, and I can write down what cos x is. SOHCAHTOA, sine is opposite over hypotenuse, so sine x is 4/5, cos is adjacent over hypotenuse, cos is 3/5. So I can substitute them in here and do 2 times 4/5 times 3/5. So 2 times 4/5 times 3/5, 2 4s are 8, 3 8s are 24. So it gives me 24 on the top of my fraction there. And then I've got 5 5s on the bottom. Excuse me, 25 on the bottom. So 24 over 25. So sine 2x is done this way. Now, if we were to do the same for cos 2x, the issue is we've got 3 possible expansions for it. So we've got cos squared x minus sine squared x. We've got the 1 minus 2 sine squared x. And we've also got the 2 cos squared x minus 1. So we've got 3 different versions here. However, it doesn't matter which one we use, we should get the exact same answer regardless. So I'm going to take the 1 minus 2 sine squared. Let's imagine we do that way. So 1 minus 2 sine squared x. We know what sine is. Sine is 4/5. So I get 1 minus 2 times the sine squared, so 2 times 4/5 squared. So I get 1 take away 2, well 4/5 gives you 16 over 25. So I end up getting 1 take away 32 over 25. End up giving me negative 7 over 25. I should get the same answer regardless of which version I use. If I use the 2 cos squared minus 1, 2 cos squared x minus 1, I would get 2 times 3/5 squared, take away 1. 3/5 squared gives you 9 over 25. 2 of those is 18 over 25. Take away 1. Lo and behold, that also gives me the negative 7 over 25. When it comes to the cos 2x, it doesn't matter which version you use. The key thing is to use the version which makes it the simplest calculation for you and which is most relevant to the question. Using these double angle formula is vital. We have to be able to work with them, we have to be able to use them. Most importantly, we have to be able to understand them and remember them.